Let's practice the chain rule. Practice, practice, practice. Many of these mathematical concepts require a fair amount of practice before they become intuitive. So we're going to do 4 or 5 problems here as examples of the chain rule. So in these problems, let's identify the function f of x as a composition of two functions g of x and h of x, and write out the derivatives of both g of x and h of x, and then use the chain rule to put it all together. Suppose f of x is cosine of 1 minus 4x. I'm going to think of f as g of h, where h is the inside function and g is the outside function. Here, h of x is 1 minus 4x, and g of x is cosine x. This function f can be thought of as first computing 1 minus 4x, and then after that's done, computing the cosine. Now we know the derivative of 1 minus 4x is minus 4. Derivative of cosine is minus sine. So by the chain rule, the derivative of the cosine of this 1 minus 4x is negative sine of this 1 minus 4x times the derivative of that inside part. The derivative of 1 minus 4x is minus 4. So there's my answer. The minus sign cancel out, and I get 4 sine of 1 minus 4x. Here's another function. Let's work with the square root of x squared plus 4. Notice that there's no way to simplify this. I can think of this function as being g of h, where the inside part h is x squared plus 4, and the outside part is the square root function. Since the derivative of x squared plus 4 is 2x, and the derivative of the square root function is 1 half x to the minus 1 half, then by the chain rule, the derivative of the square root of x squared plus 4 is 1 half x squared plus 4 to the minus 1 half. That is involves the derivative of the square root. And then since this inside part, x squared plus 4, is not x, we need to multiply by its derivative, 2x. So the derivative of x to the 1 half is 1 half x to the minus 1 half. The derivative of the square root of x squared plus 4 is 1 half x squared plus 4 to the minus 1 half times 2x, derivative of the inside part. That's the chain rule in action. I can clean that up a little bit because I have 2's that'll cancel, and there's my answer. Another problem. Suppose I have x cubed plus cosine x all to the 4th power. Think of this as an inside part that's x cubed plus cosine, and an outside part that is the 4th power function. So I'm going to think of h, the inside part, this way, and the outside part as the 4th power function. I know how to take the derivative of the inside part. It's 3x squared minus sine x. The derivative of the outside part is 4x cubed. So by the chain rule, the derivative of this quantity to the 4th power is 4 times that quantity cubed times the derivative of that inside part. We did this in another lecture. It's worth doing again. A more complicated composition of functions. If I have 3 to the tangent of something, I know how to take the derivative of 3 to the x. That's the outside function. I know how to take the derivative of tangent. That's the next one inside. I know how to take the derivative of the square root, and I know how to take the derivative of x squared plus 9. Putting these all together, the derivative of 3 to the x is natural log 3 to the whatever. The derivative of whatever is secant squared of this junk. The derivative of that junk is 1 over 2 square root of x squared plus 9, but the derivative of x squared plus 9 is 2x. So by the chain rule, I get natural log of 3 times 3 to the tangent of all of this times secant squared of this times 1 over 2 square root 2x. I can, by the way, get the 2's to cancel, clean it up, and there is, I think, my final answer. What a mess. We can use the chain rule to find derivatives of inverse functions. If I have something like the arctangent and I want to take its derivative, there's a little trick I can do. I can rewrite an inverse function. If y is the arctangent of x, then x is the tangent of y, and I can differentiate here immediately, but I have to differentiate this with respect to x. So I'm going to differentiate both sides of this equation with respect to x. By the chain rule, the derivative of tangent y with respect to x is the secant squared of y times the derivative of y. Why is there a y prime here? The chain rule says that when you take the derivative of tangent y, since it's not tangent x, you're going to get secant squared y times the derivative of y. Now, if I look at that original equation and I differentiated both sides, well, the derivative of x on the right side was 1. So if tangent y is x, if I have this expression here and differentiate with respect to x, I have this expression. What am I after? I'm after y prime. So let's solve for y prime, dividing both sides by secant squared of y, and there's my derivative. The derivative of the arctangent of x is this thing. Now I can clean that up a little bit because I'd like to go back to x's. So recall a Pythagorean identity. Secant squared y is 1 plus tangent squared y. Stick that in to my answer. Y prime is 1 over 1 plus tangent of y squared. But tangent y is x. Recall that from the very beginning, way up here. I can replace tangent y by x and write my answer this way. So there is the derivative of the arctangent function. It's 1 over 1 plus x squared. This topic, the derivative of inverse functions, will be the subject of our next lecture.